Let's now talk about excretion, which is the process by which the body gets rid of drugs and their metabolite. There are several ways by which this can happen, but the main one is through urines. And so urine are generated in the kidney by the renal functional unit, which is nephron. Actually. So the nephron is both anatomically and functionally distinct structure that we find in the kidney. And what happens in the nephron is that the bloodstream through capillaries makes contact with the start of the tubules that end up collecting urine into the bladder. And what we have here is very leaky capillaries that basically filtrate out everything that is liquid or contains molecules with a molecular weight of less, not more, than 20 kilodaltons. Once the liquid is filtrated through, throughout the tubule, which is long and wraps around the nephron and is in contact with the capillaries, we have active reabsorption of water throughout the length of the nephron. And that's how we avoid dehydration, basically, because the kidneys filtrate about 120 liters per day. So they're constantly filtrating blood. So in the proximal part of the tubule, we have secretion from the bloodstream, so from capillaries that are in contact with the tubule of small molecules. And then throughout the tubule, and again, we have the reabsorption of water. And finally, in the distal part of the tubule, we have reabsorption of lipophilic drugs. So let's look at filtration a little bit more in detail. The most important thing is that blood proteins, including proteins that bind drugs in the bloodstream and blood cells, are not filtrated through the tubule, so they remain in the bloodstream, and that's important. However, when the kidney is dysfunctional, we can find that a percent of those proteins make it their way to the urines, and that's how we know that the kidney functionality is impaired. Importantly, the glomerular filtration rate, or GFR, is one of the parameters that will help us determine how long a drug resides in the bloodstream. And basically, it's the rate at which a nephron in the kidney filtrates blood. Now, let's look about let's look at the process of tubular secretion, which is an active process that happens in the first portion of the tubule, the one closer to the glomerule. And what happens here is that through two distinct transporter systems, molecules that are weak bases and molecules that are weak acid get secreted into the urine. So because it's an active transporter, it can be saturated in the presence of other molecules. And so, for example, sometimes we will add to the administration of penicillins, we will add probenecid, which is a compound used in the treatment of gout, and basically helps the secretion of uric acid, and also happens to compete with the penicillin for the transporter for weak acids. So in the absence of probenecid, penicillin gets secreted out relatively fast, and so is eliminated through the urine for in a relatively short time. In the presence of probenecid, that competes with for the transporter, we have an increase in the lifetime of penicillin in the blood, in the plasma, because again, probenecid is competing out, and so penicillin is not secreted at the same rate. The other important phenomenon is tubular reabsorption that happens in the distal portion of the tubule, so far away from the glomerule. And so in this case, what happens is that molecules that are lipophilic and uncharged get reabsorbed into the bloodstream. This is important for drugs that are weak bases, such as amphetamine, because this phenomenon means is that if we have an equilibrium between acid and base form of the drug, we know that only the uncharged form of amphetamine will be reabsorbed in the distal portion via this lipophilic transporter. For this reason, the pH of urine will influence the lifetime of amphetamine and the rate of excretion. So here, if we look at urinary excretion per day, we see that when urines are acidic, then amphetamine gets excreted pretty fast. By the second day after administration, it's almost completely out. When urine is basic, instead, very little of amphetamine gets secreted out. This can be seen also by looking at the plasma concentration. So for this reason, when urine is acidic, the plasma concentration of amphetamine is low very quickly. So within a day or most of it is out. When urine is basic, on the other hand, the plasma concentration stays stays high for 3 to 4 days. Okay, so with that, we've kind of looked at the main factors that influence kidney filtration and how we can assess and influence really the rate of excretion. Another route that is important is the bile. And so what we find is that from the liver, especially the product of phase 2 metabolism with the glucuronidation of a drug, gets secreted out into the bile by active transport and from the bile into the GI tract. Here, the drug can be either excreted in fishes or in the case where it's cleaved out and basically, cleaved off from the glucuronidation, and so it's back in the free form, it can be reabsorbed by passive diffusion into the bloodstream, go through the liver again, and then go through systemic circulation. Other excretion routes are pulmonary, saliva, sweat, and breast milk. And breast milk is particularly important for its potential toxicity. And so for this reason, certain drugs cannot be administered or to lactating women because drugs will be concentrated in the breast milk, which is slightly more acidic, and potentially cause harm to the newborn. The pulmonary route is another important route in which molecules that are volatile can be excreted quickly. Another parameter I want to introduce, and it's actually very important in pharmacokinetics, is the so-called clearance. So it's simply the rate of elimination of the drug relative to the plasma concentration. And so we'll define different clearances depending on the route of elimination. And together they make up the total clearance of the drug. And knowing the clearance of the drug will help us determine the half-life of the same drug. So half-life is simply, the measure of plasma concentration over time, and we define as half-life the time at which the concentration is half of the starting point. Because the decrease in concentration follows a parabolic, formula. The half-life can be calculated at any point in this curve. So the half-life is also equal to this formula where Vd is the volume of distribution and Cl is clearance. So we haven't gone through the volume of distribution in this class, but basically it's a measure of the volume to which the drug is distributed, and in turn reflects whether a drug is lipophilic or hydrophilic. So with that, let's revise something that we have seen early on in the class. And so the fact that, failure in drug development is often due to pharmacokinetics of the drug. And for that reason, what we'd like to do is be able to predict the ADME properties of the drug before even, uh, finalizing the formula of the drug. In other words, as soon as we have from high throughput screening, we have some hits, we can develop lead compounds to optimize their ADME properties. And we can do that in silico, and we'll see, especially in the next module, how we can help predict the properties of the drug based uniquely on their structure. This leads us to define the so-called Lipinski rule of 5, which is at the basis of in silico predictive ADME. It's actually an empirical parameter discovered by Lipinski, and basically helps us predict whether a lead compound will be a good drug, whether will be favorable ADME properties based on several factors, four main factors. So the Lipinski rule of 5 states that for poor absorption and permeability will occur, so poor ADME will occur if a molecule has a molecular weight greater than 500, log P more than 5, and we'll see log P in a second, in the next module, but basically it's a measure of hydrophobicity. If the hydrogen bond donors are more than 5, and those are expressed as numbers of hydroxy groups and amine groups. And if the hydrogen bond acceptor groups are more than 10. And this is expressed again as a sum of nitrogens and oxygen in the molecule. So let's look at a few examples of drugs that are currently in the market. They all tend to have relatively small molecular weight. Gleevec, which is a tyrosine kinase inhibitor, is pushing the limit, getting very close to 500. If we look at their log P, so their hydrophobicity, all of them are well below 5, with the exception of Gleevec, which again is the one with the highest value for log P. If we look at the number of hydrogen bond donors, they're all well below 5. And if we look at the number of hydrogen bond acceptors now, they're all below 10. This is a general observation that has been made, and basically helps us in evaluating a drug, or rather a lead compound for a drug. So in conclusion, we can see that many factors lead to developing a viable drug. And some of the things we need to consider are, again, molecular weight, pKa, hydrogen bonding property, lipophilicity, solubility, how they bind to plasma protein, the metabolism, membrane permeation, and the rate by which it's dissolved. And then these other pharmacokinetic parameters that together make up the half-life and the oral availability of the drug.